The Boötes Void is identified as a vast region of unusually low galaxy density located in the direction of the constellation Boötes. Its recognition emerges from systematic surveys that map the positions and distances of galaxies across large portions of the sky. In these surveys, galaxies are not evenly spread. They trace a web-like pattern of filaments and walls that surround expansive cavities. The Boötes Void is one of the most prominent of these cavities first noted because of how sharply it contrasts with the surrounding concentration of galaxies. When astronomers chart redshifts, which are shifts in the colour of light caused by cosmic expansion, they can infer distances and build a three-dimensional picture of the nearby universe. In that picture, the Boötes Void appears as a roughly spherical or slightly elongated region, with far fewer galaxies than expected for its volume. The centre of the Boötes Void lies at a distance of several 100 million light-years from Earth. Its diameter is estimated to be on the order of 300 million light-years, making it one of the largest known voids in the local universe. This scale is not measured directly by seeing an edge, but by identifying where galaxy counts drop significantly below the average and then rise again as one moves outward. The void is defined statistically not as an absolute emptiness, but as a region where the number of galaxies per unit volume is dramatically lower than in typical cosmic environments. Even at its sparsest, it is not perfectly empty. A small number of galaxies are known to reside within it, but their scarcity is what makes the region stand out. The process of locating the Boötes Void depends on careful cataloguing of galaxy positions. Early surveys relied on optical telescopes that recorded galaxy images on photographic plates. Astronomers measured apparent brightness and redshift, then inferred distance. When plotted, the data revealed large-scale patterns. In the case of Boötes, observers noticed a conspicuous gap in the distribution. Later surveys with more sensitive detectors and larger sky coverage confirmed that the gap was not an artifact of missing data or observational bias. It persisted across different wavelengths and survey methods, reinforcing the conclusion that a genuine underdense region existed there. To define the void, astronomers compare local galaxy density to the cosmic average. The average is derived from counting galaxies across large volumes and smoothing over smaller fluctuations. A void is then identified where the density falls below a chosen threshold, often a fraction of the mean. In the Boötes region, the density drops to only a few % of the average. This makes it an extreme example, not just a mild dip in density, but a deep depression in the cosmic web. The boundaries of the void are irregular, shaped by the surrounding filaments and walls that contain clusters and groups of galaxies. These boundaries are traced by sharp increases in galaxy counts. As one moves outward from the centre, the constellation Boötes serves only as a line-of-sight reference. The void itself spans a range of distances along that direction, extending both nearer and farther than the stars that outline the constellation in the night sky. From Earth, the void is not visible as a dark patch because the night sky is dominated by nearby stars within the Milky Way. Its presence is revealed only through mapping distant galaxies and noting where they are absent. This distinction is important because the void is not a hole in the sky, but a feature in three-dimensional space embedded within the expanding universe. Locating such a void also requires correcting for observational limits. Telescopes can only detect galaxies brighter than a certain threshold. Faint dwarf galaxies may escape detection, especially at large distances. To account for this, astronomers apply corrections based on survey depth and completeness. In the case of the Boötes Void, multiple surveys with different sensitivities have been compared. Even when accounting for faint galaxies, the region remains unusually empty. This consistency strengthens confidence that the void is real, and not merely a consequence of limited observations. The size of the Boötes Void places it among the largest structures known that are defined by absence rather than presence. Galaxy clusters and superclusters are defined by concentrations of mass and light. Voids, by contrast, are defined by what they lack. Yet they are just as much a part of cosmic structure. Their sizes and distributions carry information about how matter evolved from the nearly uniform conditions after the early universe into the complex web seen today. The Boötes Void is therefore not an anomaly simply because it is large. Large voids are expected in a universe shaped by gravity, acting on initial density variations. What makes Boötes notable is how extreme its underdensity appears when measured. When astronomers speak of the Boötes Void not fitting a model, the first step is always to establish its basic location and scale with precision. Without a clear definition of where the void is and how large it is, claims of tension with theory have no foundation. Over decades of observation, the position and approximate dimensions of the Boötes Void have remained stable. New surveys refine the edges and occasionally add faint galaxies to the census, but the overall picture persists. There is a large region in that direction where galaxies are rare, and its volume is substantial compared to typical voids. This region exists within the broader context of the cosmic web. It is not isolated from the rest of the universe. Galaxies at its boundaries trace arcs and sheets that curve around the empty interior. These surrounding structures help define the void's shape, and also influence its evolution through gravitational interaction. To understand any apparent mismatch with models, one must begin here with a careful, grounded description of where the Boötes Void is, how it is identified, and how its size is measured. Only with this foundation can further questions about its contents and behavior be meaningfully addressed. Observing a void begins with observing everything around it, because a void is not a visible object with a surface that reflects light. It is a pattern in the distribution of galaxies, and that pattern is inferred from surveys that measure where galaxies are and how far away they are. The core measurement is a galaxy's position on the sky and its distance along the line of sight. Position comes from imaging, where a telescope records the faint glow of many galaxies across a defined area. Distance is usually inferred from the way the galaxy's light is stretched to longer wavelengths by the expansion of the universe, a shift known as redshift. Redshift is not a direct reading of kilometers, but a measurable change in a spectrum where familiar features in the light appear displaced. When the redshift is small enough that local motions do not dominate, it provides a practical distance indicator through the relationship between distance and recession speed expected from cosmic expansion. In a survey, thousands or millions of galaxies are imaged. Then a subset is targeted for spectra, because spectra take more observing time than images. The result is a three-dimensional map in which each galaxy is a point, with coordinates 2 angles on the sky and 1 inferred distance. A void appears when those points become sparse across a volume that would otherwise be expected to contain many more galaxies. This approach does not rely on any one galaxy, but on statistics across large samples, because the absence of galaxies must be distinguished from gaps created by incomplete observing. That distinction drives much of the careful work behind void claims. The first practical limitation is brightness. Telescopes have detection thresholds, and a galaxy must be bright enough to be recorded against the background of the night sky and the detector's own noise. For distant galaxies, brightness falls with distance and faint galaxies drop out first. This creates a selection effect in which the farthest parts of a survey contain only the brighter galaxies. If a region of space contains mostly faint dwarf galaxies, a shallow survey might mistake it for emptiness. Surveys address this by defining a sample that is complete above a chosen brightness limit within a chosen distance range. Within that range, the survey aims to detect all galaxies brighter than the limit regardless of where they sit on the sky. The chosen brightness limit is not arbitrary because it shapes what the survey can say. A conservative limit provides higher confidence and completeness, but it discards faint galaxies that might live in low-density environments. A deeper limit includes more galaxies, but only if the observing and data processing truly reach that depth uniformly. For void studies, uniformity matters as much as depth, because a patch of poorer data quality can mimic a void. Observers track this by measuring exposure time, sky brightness, atmospheric conditions, and detector performance across the survey footprint, then building maps of completeness that show where the survey is strong and where it is weak. A second limitation is that a galaxy is not a point source. It can appear extended, diffuse, and low in surface brightness, meaning its light is spread over a large area on the detector. Two galaxies with the same total brightness can be differently detectable depending on how concentrated their light is. Low surface brightness galaxies are especially challenging, and they are relevant because void environments may host small faint systems with weak star formation and diffuse light. Imaging pipelines can miss these galaxies or misclassify them as noise, foreground features, or artifacts. Surveys mitigate this by tuning detection algorithms using deeper imaging in selected areas to estimate what is missed and cross-matching with observations in other wavelengths. Radio observations can detect cold hydrogen gas, even when starlight is faint, offering a complementary path to finding galaxies that optical surveys undercount. Infrared surveys can also reveal stellar populations obscured by dust, although dust is usually a larger issue in star-forming regions than in the sparse interiors of voids. Each wavelength has its own biases, and the most reliable void statements come from combining them rather than relying on a single type of map. Distance estimates introduce their own complications. Redshift is influenced not only by cosmic expansion, but also by local motions called peculiar velocities that add to or subtract from the expansion signal. In dense regions, peculiar velocities can be large stretching clusters along the line of sight in redshift space, and producing distortions that are not true physical elongations. In under-dense regions, peculiar velocities tend to reflect outflow from the void interior, but the magnitude is still a source of scatter. When a void is mapped, its apparent shape can be altered by these effects. Analysts often work with models that convert observed redshifts into estimated real space positions, but these conversions depend on assumptions about the velocity field. Even without complex corrections, careful void work acknowledges that the map is built in redshift space, a space that is directly observed but not identical to true physical positions. This is not a flaw but a fact about what is measured, and it affects how sharp a void boundary can ever appear. Survey geometry is another source of false emptiness. A survey does not observe the entire sky uniformly. It has edges, masked regions around bright stars, and gaps where data quality is poor. If these geometric features are not handled correctly, they can carve holes in the galaxy distribution that look like voids. To prevent this void, finding algorithms incorporate the survey mask a description of where the survey has usable data and where it does not. They also use random catalogues, synthetic sets of points that follow the same angular selection as the real survey, to correct for geometric effects when measuring densities and correlations. The idea is to compare galaxies to a fair reference that represents where galaxies could have been observed. If an apparent void aligns with a masked region, confidence drops. If a void persists in independent surveys with different masks and observing strategies, confidence rises. Once a survey map is built, defining a void is a matter of choosing a density threshold and a method to locate contiguous under-dense regions. Some methods smooth the galaxy distribution onto a grid estimating a density field, then identify basins where the density is below a chosen level. Other methods use geometric constructions based on distances between galaxies, finding large empty spheres or more complex shapes that fit between the points. The choice of method influences the resulting void catalogue. A method that looks for maximal empty spheres tends to highlight the emptiest cores, while a method that follows density basins can produce larger, more irregular void boundaries. For the Boötes Void, early identification is largely visual and statistical, based on a striking deficit in a region of the map, but modern analyses still face the general issue that a void's measured size depends on a definition. This does not mean the void is not real. It means the void has no single sharp edge in nature, only a gradual transition from lower density to higher density, and the chosen threshold sets where the boundary is drawn for measurement. Observations also have to separate nearby foreground structures from the distant volume that contains the void. The Milky Way's own stars and dust obscure parts of the sky, and in those directions galaxy surveys are incomplete. For Boötes, the relevant sky region is away from the densest parts of the Milky Way's plane, which helps, but even then there are patches of extinction where dust dims background galaxies. Surveys correct for this by using dust maps derived from the colours of stars and by adjusting detection thresholds accordingly. If these corrections are not applied, a dusty patch can appear as a dip in galaxy counts. Again, the safeguard is redundancy. If different surveys using different instruments and different analysis pipelines recover the same under dense volume in the same place and at the same distance range, the case for a genuine void strengthens. The phrase that something found in the Boötes Void does not fit any model often begins as a reaction to a sparse map that shows an unexpectedly large gap, or to a small set of galaxies inside the gap that appear unusual. Before any physical interpretation observation must confirm what is actually present and what is absent. That confirmation is slow and methodical. It asks whether the relevant galaxies are within the survey's complete sample, whether low surface brightness systems could have been missed, whether the distance estimates place the galaxies correctly, and whether the survey geometry or dust could create a false cavity. It also asks whether the void is being compared to a fair baseline because a shallow survey cannot be judged against expectations built for a deeper one. Observing a void is not the act of seeing nothing. It is the act of measuring faint light, measuring spectra, building catalogues, tracking selection, and testing whether the emptiness remains after every known bias is accounted for. Only then does the void scarcity become a meaningful piece of information about the universe's structure. The Boötes Void is not defined by a sharp boundary in space, but by a transition from very low galaxy density to the richer pattern of the cosmic web. To understand the void, the outermost region to examine is the surrounding structure that frames it, because the rim sets the reference level against which the interior is judged. In galaxy maps, the space around the void shows the familiar features of a large-scale structure. Galaxies gather in groups, groups gather in clusters, and clusters connect along elongated filaments and sheet-like walls. These features are not decorative. They are the visible outline of the underlying mass distribution dominated by dark matter that has grown from small early density differences. In the direction of Boötes, surveys reveal concentrations of galaxies that arc around the underdense centre, suggesting that matter has flowed outward from the region that becomes the void and accumulated along the edges. This is a general expectation for voids. Under gravity, denser regions pull in matter, while under dense regions lose matter, relative to the average effectively emptying as the universe expands. The edges become comparatively crowded, not because they are uniquely active, but because they are where displaced matter ends up in the cosmic web's geometry. The rim is often described in terms of walls and filaments. A filament is an elongated structure where galaxies and groups align, tracing an underlying dark matter strand. A wall is a broader sheet, a planar arrangement of galaxies that can span tens of millions of light-years. Around a large void, walls and filaments can form a partial enclosure. They rarely form a complete shell because the cosmic web is not a set of closed bubbles. Instead, it is a connected network with openings and passages. In maps of the Boötes region, the boundary looks like an uneven ring when projected on the sky. but in 3 dimensions it resembles an irregular basin in the density field. This matters for interpretation. If the boundary is irregular, then the interior is not equally empty in all directions. Some lines of sight may pass through a deeper underdensity, while others graze near filaments that intrude inward. A statement about what is inside the void must therefore specify how the void is defined and which part of the interior is being considered, because the density can change gradually from the rim to the center. Galaxies near the boundary behave differently from galaxies in the deepest interior. At the edge, the local environment includes nearby neighbors and a stronger tidal field, meaning a stronger gravitational influence from surrounding mass. Tides can shape galaxy orbits within groups, alter gas inflow and drive interactions. The boundary region can also contain small groups that form where filaments intersect walls. These groups are not as massive as rich clusters, but they still host multiple galaxies and can influence one another through gravity and gas dynamics. In contrast, the deepest interior is expected to host mostly isolated systems. This contrast is one reason the rim is essential to describe first. It is the outer context in which the void is embedded, and it helps separate effects that arise from isolation from effects that arise from being near larger structures. The walls and filaments also affect how the void is measured in redshift surveys. Redshift distortions caused by galaxy motions tend to be stronger in dense environments, where velocities within groups and clusters are high. These distortions can elongate clusters along the line of sight in redshift space, making edges look thicker or more smeared than they are in real space. If a void boundary is drawn based on redshift space density, it may include some of this smearing. Analysts account for this by smoothing on scales large enough that small distortions average out, and by using methods that are less sensitive to the details of cluster shapes. For the Boötes region, the void is so large that the boundary is defined on scales where these effects are secondary, but they still influence the fine structure of the rim and the apparent depth of the void when measured in a catalogue. The matter distribution around the void is not only made of galaxies. Much of the mass is dark matter, and much of the ordinary matter is gas that does not shine brightly in visible light. The rim is expected to contain warmer and denser gas than the interior, because gas falls toward higher density regions and is compressed and heated by gravitational collapse. In the outer regions around Boötes, gas can exist in filaments as a diffuse warm medium, and it can be hotter in groups where gravity is stronger. This gas can be detected indirectly through absorption lines in the spectra of background sources and through faint emission in some cases. While such measurements are challenging, they matter, because they tell whether the rim contains the amount of baryonic matter expected from models, and whether the void interior is connected to the rim by low-density channels that can transport gas. A void is not sealed. Material can flow along filaments and through sheets, and the rim is the place where these flows are most structured. The rim is also the region where the void's influence on galaxy motions can be observed most clearly. In the standard picture, galaxies near a void experience a net gravitational pull away from the underdense region, because there is less mass inside the void to slow expansion and less gravitational attraction toward the center. This creates an effective outflow, where galaxies tend to move away from the void center relative to the general expansion. This motion is subtle, because the overall cosmic expansion dominates, but it can be detected statistically by comparing observed redshifts to distance indicators or by measuring coherent distortions and clustering. The outflow tends to pile up matter at the boundary-enhancing walls and filaments. The result is a rim that is not just a passive outline but a dynamically related structure. The boundary and the interior evolve together with the rim, reflecting the history of matter evacuation from the center. When claims arise that something in the Boötes void does not fit any model, they often focus on an interior feature, but the credibility of the claim depends on the rim. If the boundary is misidentified, the interior sample may be contaminated by galaxies that are actually in filaments near the edge. If the rim is defined differently in different analyses, the measured void size and depth can change, affecting how unusual the interior appears. A very large void defined with a low threshold may include moderately underdense regions that still contain filaments and groups. A smaller void defined around the deepest minimum may appear more extreme, but represent a different object. This is why careful void work often separates the core, the inner region, and the boundary zone rather than treating the void as a single homogeneous entity. The cosmic web around Boötes also offers a check on whether the void is consistent with the broader distribution of voids. In the standard cosmological picture, voids occur at many scales, and large voids are rare but expected. Their rarity is linked to the statistical distribution of initial density variations and to how those variations grow. The rim's structure, including how sharply density rises and how connected the surrounding filaments are, provides information about the void's formation history. A void with an unusually sharp boundary might suggest an especially coherent evacuation, while a void with a ragged boundary and deep intrusions might suggest a more typical, gradually formed underdensity. Observations of the Boötes boundary show irregularity in connectivity features that align with a web-like universe rather than a set of isolated bubbles. At this outer layer, the key point is that the Boötes void is framed by matter, not by nothing. The walls and filaments around it are the visible manifestation of the mass that has been displaced relative to the void interior. They define the void shape, they influence how it is measured, and they provide the environment against which interior properties must be compared. Establishing this rim is part of proceeding from outer to inner. The boundary is the first inward step after locating the void itself, and it sets the baseline that allows later examination of what lies deeper within the underdense volume, without confusing true interior phenomena with edge effects. The origin of a giant void is traced back to conditions that are already set long before any galaxy forms. In the early universe, matter and radiation are distributed almost uniformly but not perfectly. Small variations in density exist as gentle ripples, with some regions slightly denser than average and others slightly less dense. These differences are tiny at first, but gravity acts on them continuously. Regions that start denser attract more matter and grow denser over time, while regions that start underdense attract less matter and become relatively emptier as the universe expands. A void is the large-scale outcome of an underdense region that expands more quickly than its surroundings. The word expands here is not a separate expansion from the universe's overall expansion, but a relative change in the local pattern of matter. In an underdense region, there is less gravitational pull inward, so the outward Hubble flow, the general recession of matter with distance, is less slowed. Over billions of years, that difference accumulates. Matter streams away from the underdense center toward the surrounding denser regions, reinforcing filaments and walls, and leaving behind a broad cavity in the cosmic web. A useful way to picture the process without relying on metaphor is to treat the early density field as a landscape of small rises and dips. Gravity causes matter to flow down the gradient of gravitational potential, which is linked to density. In an underdense region, the potential is higher than in nearby overdense regions, so matter tends to move away toward the lower potential wells of denser areas. This flow is slow on human timescales, but decisive over cosmic timescales. The result is that voids are not carved out by any sudden event. They emerge as a natural consequence of gravitational evolution in an expanding universe. The scale of a void depends on the scale of the initial underdensity and on how it is embedded in the surrounding pattern. Smaller voids can merge into larger ones as walls between them thin out and dissolve. This merging process helps produce very large voids, because the cosmic web is not static. Its topology changes as structures grow, and under dense basins can connect, creating a larger contiguous region of low density. In standard cosmology, the initial density variations are described statistically. They're often modelled as a random field with a known power spectrum, meaning a known distribution of fluctuation strength across different length scales. That distribution is constrained by observations of the cosmic microwave background, the ancient radiation that fills space and carries an imprint of early density ripples. The microwave background shows that fluctuations are small and nearly scale invariant across a wide range of scales, meaning there are variations on many sizes. Gravity then amplifies these variations differently, depending on scale and environment. On smaller scales, dense regions collapse to form halos, which are gravitationally bound structures dominated by dark matter. On larger scales, the growth is slower and produces the web pattern of filaments, walls, and voids. A large void like Boötes corresponds to a fluctuation on a very large scale, or to the merged outcome of multiple smaller fluctuations. Either way, the key is that large voids are rare because very large coherent underdensities are statistically uncommon in the initial field. Rare does not mean impossible. It means that in a sufficiently large universe, some extreme structures will exist simply because the volume sampled is large. The evolution of a void can be described in stages that proceed from its outer environment inward, but in time the process is continuous. Early on, the region that becomes the void is only slightly underdense. Galaxies and halos have not yet formed, so the distinction is purely in mass distribution. As time passes, matter flows outward, and the density contrast grows. The boundary becomes more pronounced because denser surroundings continue to gather matter, while the interior continues to lose it relative to the mean. In simulations, void interiors become dominated by low-density dark matter and diffuse gas with a network of tenuous filaments that may persist inside but are weaker than the external web. Some dark matter halos still form within the void, but they are fewer and typically less massive. This is because the growth of halos depends on having enough matter in a region to collapse. In an underdense environment, collapse is delayed or suppressed, so the halo mass function, the distribution of halo masses, shifts towards smaller sizes. This changes what kinds of galaxies can form there because galaxies form within halos. The expansion history of a void is also influenced by dark energy, the component of the universe that drives accelerated expansion at late times. Dark energy affects all regions by changing the overall rate at which structure growth proceeds. Once dark energy becomes dominant, the growth of density contrast slows because cosmic expansion pulls matter apart more rapidly relative to gravity's ability to gather it. For voids, this means their relative evacuation continues, but the rate at which structure evolves changes. The void becomes more stable in the sense that large-scale patterns stop changing as quickly, though local motions persist. This late-time influence matters for interpreting present-day voids because it shapes the expected density profiles and the velocity field around voids. A present-day void is the outcome of gravity acting under a time-dependent expansion rate, not a simple emptying under a constant background. A large void can challenge intuition because it seems like an absence that must be explained by an unusual cause. In the standard framework, the cause is not unusual. It is the same gravitational physics that creates clusters and filaments. The difference is the sign of the initial fluctuation. Over dense regions become crowded, under dense regions become sparse. What can create tension with models is not the existence of a void, but its specific properties, its size, its depth, its shape, and the distribution of whatever galaxies and gas remain inside. To evaluate those properties, one must know what the model predicts, given the initial fluctuation statistics and the growth history. Simulations provide those predictions by evolving dark matter and gas forward in time from initial conditions consistent with the microwave background. In these simulations, voids appear naturally. They have a range of sizes. Some are large enough to be comparable to Boötes. The predicted abundance of such large voids depends on the assumed cosmological parameters and on how voids are defined. A definition based on galaxy counts can yield different void statistics than a definition based on total mass density, because galaxies are biased tracers. They are more likely to form in denser regions, so the galaxy-defined void can appear larger and emptier than the mass-defined void. This difference is not a failure of the model. It is a reminder that observation uses light as a proxy for mass, and that proxy has rules. Void merging adds another layer. If two underdense basins expand and the wall between them thins, they can effectively join, producing a larger composite void. In practice, this can happen gradually, with the boundary becoming less distinct and the interior becoming a broader underdensity. A very large void may therefore be a product of environmental history, not just a single primordial fluctuation. In the case of Boötes, its prominence suggests a deep underdensity in a region where surrounding structures have grown enough to emphasize the contrast. The existence of a few galaxies inside is expected because even an underdense region contains matter. The question is whether the number and properties of those galaxies and the inferred mass distribution match the statistical expectations of structure formation. At this stage, the focus remains on formation at large scale, still closer to the outer context than to any detailed interior phenomenon. A void forms because of how gravity responds to initial conditions in an expanding universe, and because underdense regions expand relative to their surroundings. This process creates the broad cavity in the surrounding rim. With this origin in place, the next inward step is to compare what models predict should remain inside such a cavity to what is actually observed there, using careful definitions that respect how galaxies trace the underlying mass. Once the void is located, observed, and placed within the surrounding cosmic web, the next inward region is the broad interior, as models describe it before focusing on the specific objects that have been catalogued there. A model prediction for a void interior is never a prediction of absolute emptiness. It is a prediction of relative scarcity expressed in terms of density. Contrast the fraction by which the matter density falls below the cosmic mean, and in terms of the kinds of structures that can still form when the background density is low. In the standard picture, a very large void contains dark matter and ordinary matter, but at a lower density than average. That lower density changes the statistics of dark matter. Halos changes the abundance of galaxies and changes the thermal and ionization state of the diffuse gas that fills most of intergalactic space. The expectations are built from simulations of structure formation and from analytic models that describe how underdense regions evolve. In a simulation that tracks dark matter alone, a void interior contains a web of dark matter that is thinner and less connected than outside. The dominant feature is the absence of massive halos. Massive halos, the kind that host bright spiral galaxies or large elliptical galaxies, are far less common in deep void interiors because they require a substantial concentration of matter. In underdense environments, collapse proceeds more slowly, and regions that might form a massive halo in average density space may never reach the threshold for rapid growth. Instead, voids are expected to host mostly low-mass halos. These halos can exist in relative isolation, separated by large distances. Some may align along faint internal filaments that are remnants of the early density field, but these filaments are weak. The halo population is not zero, it is shifted. This shift is a core model prediction, and it connects directly to what observers look for: fewer luminous galaxies, more dwarfs, and a larger fraction of galaxies that are small gas rich and low in stellar mass. When ordinary matter is included, the picture becomes more complex. Ordinary matter, often called baryonic matter, includes gas that can cool, condense, and form stars, and it can be heated by shocks, radiation, and feedback from galaxies. In a void interior, the gas density is low, so cooling can be inefficient because cooling rates often depend on density. Gas that is too diffuse may not cool enough to collapse into a galaxy, even if it sits inside a small dark matter halo. This can suppress star formation and create halos that are dark, meaning they contain little or no visible starlight. Models therefore predict that voids contain more low-mass halos that never become luminous galaxies. This is important for interpreting void emptiness. A void can appear emptier in galaxy surveys than it is in mass, because many halos may not host galaxies bright enough to detect. In this sense, galaxies are biased traces of matter, and the bias is environment dependent. In dense regions, many halos host bright galaxies. In voids, fewer halos cross the threshold for sustained star formation. For the galaxies that do form in voids, models predict certain tendencies. They're expected to have fewer close neighbours, so they undergo fewer strong gravitational interactions and fewer mergers. This can lead to a higher fraction of disk-shaped galaxies relative to dense environments, because disks are fragile and can be disrupted by repeated interactions. Void galaxies are also expected to retain more gas if they have not been stripped by interactions with hot gas in groups or clusters. That retained gas can support star formation over long times, but the star formation rate may be low and steady rather than bursty, because the triggers for intense star formation, such as major mergers, are less common. Metallicity, the abundance of elements heavier than helium, is predicted to be lower on average for void galaxies at fixed mass, because metallicity builds up through repeated generations of star formation and through enrichment from neighbours. In isolation, enrichment proceeds more slowly. These are statistical tendencies, not strict rules, and they depend on galaxy mass and on the details of feedback, but they form the baseline against which claims of unusual void galaxy properties are judged. The diffuse gas in a void is another major prediction. Most baryonic matter in the universe is not in stars. It resides in intergalactic gas that is largely ionized, meaning electrons are separated from nuclei due to ultraviolet radiation from galaxies and quasars, and due to heating by structure formation. In void interiors, gas is expected to be cooler on average than in dense filaments, because it experiences fewer strong shocks. It is also more tenuous, making it difficult to detect in emission. Instead, it is probed through absorption lines where gas imprints narrow dips in the spectrum of a bright background source. Models predict that void absorption should show weaker hydrogen absorption on average, and fewer metal lines reflecting lower density and less enrichment. The gas is still present and it still follows the gravitational field of dark matter, but its low density means it is a subtle component observationally. A void that appears empty in galaxies might still contain a significant fraction of its expected baryonic gas in this diffuse phase. Model predictions also include the density profile of a void, which describes how density changes from the centre outward. In simulations, voids often show a relatively flat low-density core and a rising density toward the boundary, sometimes with a ridge near the edge where matter piles up. This ridge corresponds to the surrounding walls and filaments. The exact profile depends on how the void is defined and on whether the profile is measured in mass or in galaxies. A galaxy-defined profile tends to look deeper, because galaxies avoid low-density regions more strongly than mass does. This difference can create the impression that the void interior is more extreme than it truly is in mass. Weak gravitational lensing, which measures how mass bends light from background galaxies, provides a way to measure void mass profiles directly, but the signal is small and requires stacking many voids. For a single nearby void, lensing constraints are challenging. So much interpretation relies on galaxy distributions and on the assumption that they trace the underlying mass in a predictable way. Another prediction concerns dynamics. Voids are expected to have coherent outflows with galaxies and matter moving away from the centre relative to the average expansion. This produces a velocity field that can be measured statistically. The amplitude of the outflow depends on the void's depth in mass density. A deeper mass under density produces a stronger outflow. This is one route by which models can be tested. If a void defined by galaxies appears extremely empty, the model predicts a certain level of outflow. If observed motions or redshift space distortions imply a different outflow, there could be tension. However, measuring these motions precisely is difficult, so such tests often require ensembles of voids rather than a single object. With these predictions in place, it becomes clearer what it would mean for something in the Boötes void to not fit any model. The baseline model allows large voids and allows some galaxies inside them. It predicts that those galaxies tend to be small, isolated, and gas-rich, and that the interior contains diffuse ionized gas and low-mass dark matter halos. A claim of incompatibility would require that one or more observed properties lies outside the model's statistical expectations after accounting for selection effects and definition choices. That might involve the void being too large or too empty compared to what the model predicts for the surveyed volume, or it might involve the interior hosting a concentration of galaxies or a type of galaxy that should be rare there. It could involve an inferred mass profile that is deeper than allowed by the initial fluctuation statistics, or a dynamical signal inconsistent with the predicted outflow. At this inward stage, the model expectations remain general and physical rather than tied to any single catalogue. The interior is expected to be underdense in mass, more underdense in galaxies filled with diffuse ionized gas and populated by a shifted distribution of dark matter halos that often fail to form bright galaxies. These predictions set a disciplined baseline. The next step is to move from this baseline to the specific known census of galaxies inside the Boötes void, comparing the general expectations to the actual inventory and to the properties of the objects that do exist in that sparse environment. With the baseline expectations established, the next inward region is the observed inventory of galaxies that lie within the Boötes void, as defined by survey boundaries and distance ranges. This inventory is not fixed in a single list because it depends on how the void is delineated and on the depth and completeness of the surveys used. Even so, across decades of study, a consistent picture emerges. The Boötes void contains far fewer galaxies than surrounding space, but it is not empty. A small population of galaxies resides within it, often separated by large distances, and often showing properties consistent with low-density environments. The significance of this inventory lies not only in how many galaxies are found, but in what kinds they are, how they are distributed within the void volume, and how their properties compare to galaxies of similar mass in denser regions. In early catalogues, the number of galaxies associated with the Boötes void is small, on the order of a few dozen within the central underdense volume depending on the definition. Some are relatively normal spiral galaxies, while others are smaller systems. The overall scarcity is striking when plotted in 3 dimensions. Where a comparable volume outside the void would show a tangled distribution of groups and filaments, the Boötes interior shows isolated points with large gaps between them. The distribution is not uniform. Some galaxies lie closer to the edges where faint filaments may intrude inward. Others lie deeper, closer to the region of lowest density. This non-uniformity matters because it suggests that even within the void, there is a gradient from boundary-like environments to true interior conditions. An inventory that mixes edge and core objects can blur conclusions about the deepest region. So many analyses attempt to classify galaxies by their distance from the void center or by local density measures rather than by a simple in or out label. The types of galaxies within the void provide the first direct comparison to model expectations. In general, void galaxies tend to be late type, meaning disk-dominated with ongoing but often modest star formation. This is consistent with the idea that interactions are rare and disks survive. Many are gas-rich relative to their stellar mass, consistent with isolation and limited stripping. Some void galaxies show low surface brightness, indicating diffuse stellar distributions. Such galaxies can be underrepresented in optical surveys, so their detection can depend strongly on survey depth and on algorithm choices. Radio surveys that detect neutral hydrogen can reveal gas-rich galaxies that are faint optically. When such methods are applied, the void's galaxy count can increase, but the region remains under-dense compared to average. The presence of gas-rich systems is not by itself surprising. It fits the baseline expectation. The potential tension arises when particular properties appear extreme, such as unusually high gas fractions, unusually low metallicities, or star formation histories that do not match expectations for their mass and environment. A key feature of the inventory is the relative absence of massive luminous galaxies and rich groups within the void interior. This absence is broadly consistent with simulations which predict a suppressed abundance of high-mass halos. However, to interpret this absence quantitatively, analysts compare the observed number of galaxies above a chosen luminosity or mass threshold to the number expected from a random region of space of the same volume. This comparison requires careful correction for survey completeness, and for cosmic variance, the natural fluctuation in galaxy counts from one region to another. A void is by definition an extreme fluctuation, so the question is not whether it is below average, but how extreme it is relative to the distribution predicted by the model. The Boötes Void appears unusually extreme in early analyses because of how large it is and how low its galaxy density is. Later work often frames it as an extreme but not impossible case within the distribution of voids expected in a large volume universe. The inventory therefore is part of a statistical argument rather than a simple anomaly. The spatial distribution of the void galaxies also informs the question of whether the void contains internal structure. Even within void, simulations predict faint filaments and small walls composed of low-mass halos. If void galaxies align along such features, the distribution will show subtle clustering rather than a purely random scatter. Observationally, hints of internal structure can be difficult to establish because the number of galaxies is small, and small number statistics make patterns uncertain. Even so, if several galaxies appear in a loose chain or sheet, it can suggest an internal filament. This would not contradict models. It would support them because voids are not homogeneous. The model tension would arise if the interior shows a level of clustering or a type of group formation that implies more mass concentration than expected for the void's depth. Another aspect of the inventory is the environment of each galaxy. In dense regions, galaxies often reside in groups where they orbit within a shared dark matter halo. In a void interior, many galaxies are expected to be central galaxies of their own small halos with few or no satellites. Observations can test this by searching for nearby faint companions. If a void galaxy has an unusually rich satellite system, or shows evidence of frequent interactions, it would suggest either that it is not truly in the void interior, or that the local environment is more massive than expected. Many void galaxies indeed appear isolated. When companions are found, they are often few and faint. This aligns with the baseline picture, but the difficulty is that faint companions are hard to detect at the void's distance. Deep imaging is needed to make a fair statement about satellites, and the absence of detected satellites does not prove they do not exist. It sets an observational limit. The internal properties of void galaxies add more detail. Measurements of star formation are derived from ultraviolet emission, optical emission lines, infrared dust emission, and radio continuum, each tracing different timescales and components. Many void galaxies show star formation that is ongoing but not extreme. Their colours tend to be bluer than average for their mass, consistent with younger stellar populations, or sustained low-level star formation. Metallicity measurements obtained from spectroscopy of gas emission lines often indicate lower heavy element abundance at fixed mass compared to galaxies in denser regions, though the scatter is large and calibration methods matter. Gas content measured in hydrogen can be high, These trends align with isolation and slower chemical enrichment. None of this is inherently model breaking. It becomes potentially interesting only if the magnitude of the differences is larger than expected from galaxy formation models tuned to match the broader population, or if galaxies in the deepest void interior show properties that suggest unusual gas accretion or unusual suppression of star formation. An inventory also includes what is not found. In the Boötes Void, the scarcity of luminous active galactic nuclei, the scarcity of clusters, and the scarcity of bright elliptical galaxies is often noted. This too is consistent with a lack of massive halos and with fewer mergers. However, the absence of certain rare objects is difficult to interpret, because such objects are rare everywhere, and a single region may contain none even if the model predicts a small probability. The most informative absences are those tied to common objects such as the deficit of bright galaxies above a defined threshold. Those can be compared more robustly to expectations. In considering claims that what is found in Boötes does not fit any model, the inventory serves as the anchor. It grounds the discussion in specific observed objects rather than in a general impression of emptiness. The observed galaxies inside the void as a class are broadly consistent with the standard picture of void, environments sparse, isolated, often disk-dominated, often gas-rich, and often showing relatively slow chemical evolution. The tension, if any, must come from quantitative comparisons. How many galaxies are present relative to a model prediction for a void of that size? How deep the underdensity is in mass rather than in light? And whether any specific galaxy properties exceed the range expected under known physics and known observational biases. The next inward step is to focus not only on the galaxies themselves, but on the processes within them, beginning with how star formation behaves, when the surrounding environment provides so little external influence. In the deeper interior of a void, the processes that govern a galaxy's star formation unfold under conditions of extreme isolation. The surrounding density of galaxies is low, the rate of strong encounters is reduced, and the inflow of gas from large-scale filaments is expected to be weaker and less structured than in denser regions. This does not remove the need for gas to form stars. It changes how gas is acquired, how it is compressed, and how it is regulated over time. Star formation in any galaxy depends on cold, dense gas clouds that can collapse under their own gravity. The formation of such clouds requires gas to cool from warmer phases, to lose energy through radiation, and to reach densities high enough that gravity overcomes internal pressure and turbulence. In a void, the external environment offers fewer triggers and fewer disturbances, but internal processes still operate. The question is not whether star formation can happen in a void, but what pattern it takes and what limits it. The outer environment of a void galaxy is typically a diffuse intergalactic medium that is mostly ionized. Ionized gas is less able to cool efficiently at low densities, and it is also affected by the ultraviolet background, the pervasive radiation field produced by galaxies and quasars. This background keeps much of the intergalactic gas warm and ionized, especially at late cosmic times. For a small dark matter, halo in a void, the ability to pull in gas is limited by the halo's gravity and by the temperature of the surrounding medium. If the gas is too warm relative to the halo's gravitational potential, it will not settle into the halo effectively. This sets a threshold below which halos may remain gas-poor and form few stars. In denser regions, halos can sometimes draw on gas supplied by nearby filaments, and can grow through mergers helping them cross thresholds. In void interiors, growth by mergers is reduced, so some halos may never become efficient at gathering gas. This leads to a predicted population of low-mass halos that host either very faint galaxies or no galaxies at all. For halos that do acquire gas, the gas must cool. Cooling depends on density, temperature, and composition. Gas with higher metal content cools more efficiently because heavy elements provide additional radiative channels. In void, galaxies' metallicity can be lower, which can slow cooling and delay star formation. Yet void galaxies are often gas-rich, meaning they contain significant reservoirs of neutral hydrogen. Neutral hydrogen is not the same as cold molecular gas, which is the immediate fuel for star formation, but it is a precursor. The conversion from atomic hydrogen to molecular hydrogen depends on density shielding from ultraviolet radiation and the presence of dust. Lower metallicity implies less dust, which reduces shielding and makes it harder for molecular gas to form. This can suppress star formation efficiency, meaning a galaxy can have a large atomic gas reservoir but form stars slowly. Such a galaxy appears gas-rich and relatively unevolved in its stellar population. This outcome aligns with many observations of void galaxies that show modest star formation despite significant gas content. Without frequent interactions, star formation in void galaxies is less likely to be driven by major bursts triggered by mergers. Instead, it can proceed in a more self-regulated way. Internal drivers include gravitational instabilities in the disk, where the disk's own mass distribution becomes unstable and forms spiral arms or bars that compress gas. Supernova feedback from massive stars injects energy into the surrounding gas, stirring turbulence and heating the medium. Stellar winds and radiation from young stars also contribute. These feedback processes can both trigger and suppress star formation, creating cycles where gas cools, forms stars, is heated and stirred by feedback, then cools again. In a void environment, the absence of strong external perturbations can make these cycles more regular, but it can also make them more sensitive to small changes in gas inflow. If inflow is intermittent, star formation can become episodic, even without mergers, especially in low-mass galaxies, where feedback can drive gas out of the disk temporarily. Gas inflow is a central uncertainty in void star formation. In the standard picture, galaxies acquire gas through a combination of smooth accretion from the intergalactic medium and mergers with smaller systems. In dense regions, filaments channel gas efficiently toward halos. In voids, filaments are thinner, and accretion may be more isotropic and slower. Yet the void interior is not completely disconnected. There can be faint internal filaments, and gas can still flow along them. The challenge is that measuring inflow directly is difficult. Observations can infer gas supply indirectly through star formation histories, gas metallicity patterns, and the presence of extended gas reservoirs. If a void galaxy shows very low metallicity gas in its outskirts, it can suggest recent accretion of relatively pristine material. If it shows a high gas fraction and sustained star formation over long times, it can suggest that accretion has been steady but slow. If it shows a sudden starburst without an obvious interaction partner, it can suggest that internal disk processes or minor accretion events can still trigger bursts in isolation. Another factor is the absence of environmental quenching processes common in clusters and groups. In dense environments, galaxies can lose gas through ram pressure stripping, where motion through hot intracluster gas removes their gas, or through tidal stripping, where gravitational forces remove material. They can also be heated and prevented from accreting new gas by the presence of a hot, massive halo environment. In a void, these processes are weak or absent. This can allow galaxies to retain gas longer and continue forming stars at late times. This is one reason void galaxies can be relatively blue and star-forming, compared to similar mass galaxies in dense regions. The void does not necessarily enhance star formation. It reduces the mechanisms that shut it down. The expected outcome is extended low-level star formation, rather than rapid early assembly, followed by quenching. Claims that void galaxies behave in ways that do not fit models sometimes focus on extremes galaxies with unusually high gas fractions, unusually low metallicities or star formation patterns that appear too active for their inferred halo mass. Interpreting these extremes requires caution. Gas fraction measurements can depend on distance estimates and on the conversion from observed hydrogen emission to mass. Metallicity measurements depend on calibration methods that can differ systematically. Star formation rates depend on traces that respond on different timescales and can be affected by dust. In low-density environments, dust content can be low, changing how ultraviolet and infrared traces should be interpreted. Small number statistics also matter. A handful of extreme galaxies can stand out, but models predict a distribution with tails, and rare objects can appear in any environment given enough volume. A true model tension would require that extremes are too common or too extreme compared to simulations that include realistic galaxy formation physics. A deeper test involves comparing void galaxies to simulations that model not only dark matter, but also gas cooling star formation and feedback. These simulations attempt to reproduce the overall galaxy population across environments. If they succeed in dense regions but systematically fail in voids that could indicate missing physics, such as an incorrect treatment of gas accretion in low-density environments or an incorrect impact of the ultraviolet background on small halos. However, simulations also have resolution limits, especially for low-mass galaxies, and feedback prescriptions are uncertain. A mismatch in void star formation could reflect these modelling limitations rather than a need for new cosmology. Within the Boötes Void context, the importance of star formation is that it controls how visible the void interior appears. If void halos form fewer stars, the void looks emptier in optical surveys. If star formation is more efficient than expected, the void could contain more detectable galaxies than predicted. Either outcome affects claims about whether the void fits models. The most robust statements arise when star formation properties are linked to independent measures of halo mass and gas content, allowing a comparison that separates visibility from underlying mass distribution. At this inward stage, the focus remains on processes within the galaxies that occupy the void, specifically how stars form when external influences are minimal. The baseline expectation is slow extended star formation, regulated by internal feedback and limited by gas cooling and molecular formation, with fewer bursts triggered by major interactions and fewer quenching mechanisms removing gas. This framework sets up the next inward layer, which is the gas itself, including the diffuse gas that permeates the void and the more concentrated gas that fuels galaxies, and how that gas can be detected when it produces little light. Moving inward from the star-forming regions of void galaxies to the matter that dominates the void by volume, the next focus is the diffuse gas that fills the space between galaxies inside the Boötes Void. In most of the universe, the space between galaxies is not empty. It contains a thin gas, primarily hydrogen and helium, with a small admixture of heavier elements. This gas is called the intergalactic medium. In the present epoch, much of it is ionized, meaning the electrons are separated from atomic nuclei because it is bathed in ultraviolet radiation from galaxies and quasars. In dense cosmic filaments, the intergalactic medium can be compressed and heated as matter collapses under gravity, producing warmer and sometimes hotter gas. In voids, the same gas exists, but at lower density, and typically at lower temperature, though the ionization state remains high, because the ultraviolet background permeates space. The observational challenge is that low-density ionized gas emits very little light, so the void interior cannot be mapped in emission with ordinary telescopes in the same way that galaxies can be mapped. Instead, the primary method is absorption, using bright background sources as lamps that shine through the void. Absorption measurements rely on the fact that atoms and ions absorb light at specific wavelengths, corresponding to transitions between energy levels. When light from a distant quasar or galaxy passes through intergalactic gas, the gas imprints absorption lines in the spectrum. The most important tracer of diffuse hydrogen is the Lyman alpha transition of neutral hydrogen. Even though most hydrogen in the intergalactic medium is ionized, a small fraction remains neutral, and that fraction is enough to create absorption when the gas density along the line of sight is sufficient. In denser regions, Lyman alpha absorption is stronger and more frequent. In voids, the absorption is expected to be weaker and less common, reflecting lower density. Metal ions, such as ions of carbon, oxygen, and silicon, can also produce absorption lines. These metal lines trace gas that has been enriched by material processed in stars and transported into intergalactic space by winds and outflows. In void interiors, enrichment is expected to be lower, so metal lines should be rarer. This expectation is not absolute because metals can travel far over cosmic time and faint galaxies can still enrich their surroundings, but the statistical trend is toward lower metal absorption in voids. To probe the Boötes Void, gas observers seek background quasars and bright galaxies whose sightlines pass through the void volume. Each sightline samples only a narrow pencil beam through space, so building a map requires many such sightlines. This is difficult because quasars are relatively rare on the sky, and the chance that many will lie behind a specific void region is limited. When only a few sightlines exist, conclusions are uncertain and can be dominated by chance. A single strong absorber could be an internal filament intersecting the line of sight, while an absence of absorption could occur simply because the sightline misses the denser parts of the diffuse gas distribution. For this reason, void gas studies often emphasize ensembles of voids stacking many sightlines across many voids to measure average properties. For an individual structure like Boötes, the main value of absorption studies is to establish that gas exists and to constrain its density and ionization rather than to produce a detailed spatial map. Another approach to void gas is the detection of neutral hydrogen in emission at radio wavelengths. Neutral hydrogen emits a characteristic radio line at a wavelength of 21 centimeters. This emission can be used to map cold gas in galaxies and in principle in diffuse structures, but the diffuse intergalactic medium in voids is too faint to detect directly in most cases. Instead, 21 centimeter emission surveys can detect gas-rich galaxies that are optically faint, improving the galaxy inventory and indirectly indicating where denser gas resides. If a void contains more gas-rich dwarf galaxies than optical surveys find, the void may appear less empty and baryons than in starlight. Even so, the bulk of the void's baryonic matter is expected to remain in diffuse ionized form that is beyond current direct imaging in emission. The thermal state of void gas is shaped by a balance of photoheating and adiabatic cooling. Photoheating occurs when ultraviolet photons ionize atoms, transferring energy to electrons and raising gas temperature. Adiabatic cooling occurs as gas expands doing work and losing thermal energy. In underdense regions, gas tends to expand more and cool adiabatically, so it can be cooler than gas in filaments that has been compressed and shocked. Models predict that much of the void intergalactic medium lies at temperatures of tens of thousands of degrees, though there is a range. This gas is too hot for neutral hydrogen to be abundant, but not hot enough to emit strongly in X-rays. Its detectability is therefore dominated by absorption rather than emission. The degree of ionization depends on the ultraviolet background intensity and on the gas density. Lower density gas has a higher ionization fraction because recombination, the process that turns ions back into neutral atoms, is less frequent when particles rarely collide. This means that in voids, neutral fractions can be extremely low, making absorption weaker even when significant gas mass is present. The distribution of gas within a void is not perfectly smooth. Simulations show that even void interiors contain weak filaments and small density enhancements. Gas tends to follow the dark matter distribution, though pressure smooths it on small scales. Where dark matter forms a low-mass halo, gas can collect and potentially cool, forming a galaxy if conditions permit. Where dark matter forms, only a shallow enhancement gas may remain diffuse, but still slightly denser than the surrounding void medium. These internal structures can produce absorption stronger than the void average. Thus, a sightline through a void may show occasional absorbers associated with internal filaments or halos, even if the overall density is low. This does not contradict the void's emptiness. It reflects its internal texture. A major uncertainty is the fraction of baryons in voids that reside in different phases. The cosmic baryon budget includes stars, cold gas in galaxies, hot gas in clusters, and diffuse intergalactic gas. Many baryons are believed to be in a warm to hot intergalactic medium, especially in filaments where gas is heated by shocks. In voids, a larger fraction may remain in cooler photoionized form because shocks are weaker. If so, voids could be reservoirs of relatively cool ionized gas that is difficult to detect, but contributes to the overall baryon budget. This has implications for claims of model mismatch. If a void appears too empty, it may be because the luminous traces are sparse, not because baryons are missing. Absorption studies can test this by measuring column densities and comparing them to expectations. However, converting an absorption line measurement into a total mass estimate requires assumptions about ionization temperature and geometry, and these assumptions can dominate uncertainty. A weak Lyman alpha line could arise from low-density gas, or from slightly higher density gas with a very low neutral fraction, or from a small cloud with specific conditions. Thus, interpretation must remain cautious. For the Boötes Void, the key role of gas studies is to shift the discussion from what is seen to what is present. A claim that the void contains something that does not fit models might involve unusual absorption features such as stronger than expected Lyman alpha absorption in the deepest interior, or unexpected metal enrichment signals in a region thought to be pristine. It might also involve a lack of expected absorption, suggesting even lower densities than models predict. In practice, such claims depend on limited sightlines and on complex modelling of ionization, so they rarely provide decisive contradictions. More often, they provide constraints that help refine the void's density profile and its baryon content. As the analysis moves inward, diffuse gas serves as the bridge between visible galaxies and invisible mass. It occupies most of the void's volume and carries information about density, temperature, and enrichment that galaxies alone cannot provide. Yet it is also the hardest component to measure, requiring careful spectroscopic techniques and robust modelling. With the gas phase outlined, the next inward focus is the component that shapes gravity, most strongly in the void, the dark matter distribution, and how it can be inferred in a region where light is scarce. Moving inward from the diffuse gas, the dominant component shaping the Boötes Void is the distribution of dark matter. Dark matter does not emit, absorb, or reflect light in any known way that allows direct imaging, but it exerts gravity. The large-scale pattern of galaxies and gas is understood as a response to the underlying dark matter field. In a void, the key question is not whether dark matter is present, because it must be present if the region exists within a universe where matter is everywhere, but how underdense it is relative to the cosmic mean, and what kinds of dark matter structures persist inside. Models of structure formation predict that voids are regions of low dark matter density, but they are not holes. They contain a web of dark matter that is diluted with fewer and smaller halos and with weak internal filaments. Because galaxies form in halos, the galaxy emptiness is partly a reflection of the halo population. Yet the mapping from halos to galaxies is not one-to-one, especially in low-mass regimes where star formation can be suppressed. This means that a void can contain substantial dark matter structure even when few galaxies are visible. Understanding the dark matter in Boötes therefore requires separating what is inferred from galaxy counts from what is inferred through gravity itself. One gravitational method is weak lensing. When light from distant background galaxies passes through a region with mass, the mass slightly distorts the shapes of those background galaxies. In dense regions, the distortion can be stronger and can be detected around clusters. In voids, the lensing signal is subtle and often appears as a slight stretching that indicates a relative deficit of mass rather than a concentration. Detecting this requires combining many voids, so the small signal adds coherently while random galaxy shape noise averages out. For a single void like Boötes weak lensing is difficult because the signal to noise is low and because the void covers a large area on the sky, complicating the measurement. Even so, lensing as a method is important conceptually. It provides a way to test whether the void's mass under density is as extreme as its galaxy under density suggests. If lensing shows a moderate mass deficit while galaxies show an extreme deficit, the difference can be attributed to galaxy bias and to the suppression of luminous galaxies in low-mass halos. If lensing suggests an unusually deep mass deficit, that would be more challenging for models because the mass field is tied to initial conditions and growth, not to complicated baryonic physics. Another gravitational method is the study of motions. Galaxies do not follow pure Hubble expansion. They have peculiar velocities caused by gravitational forces from the surrounding mass distribution. In the standard picture matter, flows out of voids toward denser regions, producing coherent outflows. These outflows can be detected statistically through redshift space distortions, where the clustering pattern of galaxies appears squashed or stretched along the line of sight due to coherent velocities. In voids, the expected pattern is a characteristic distortion that reflects outflow. Measuring this pattern requires many galaxy traces, which void interiors lack, so the measurement often relies on galaxies near the void boundary, and on how their distribution appears in redshift space relative to the void center. The strength of the outflow provides an indirect measure of the void's gravitational potential, and thus its mass under density. If the observed outflow is weaker or stronger than predicted for the void's measured galaxy deficit, it can indicate either that the void's mass deficit differs from the galaxy deficit, or that the modeling of velocities and bias is incomplete. A third approach uses the abundance and properties of halos inferred from galaxies and from simulations. In the standard model, the dark matter halo mass function depends on environment. In voids, the mass function shifts toward lower masses and the number density drops. If galaxy surveys find fewer galaxies than predicted, one possibility is that the halo population is lower than expected, implying a deeper mass void. Another possibility is that halos exist but fail to host visible galaxies. Distinguishing these requires either gravitational probes like lensing or detailed modelling of galaxy formation in low-mass halos. Observations of gas-rich dwarf galaxies can also help because they trace low-mass halos that might be missed in optical surveys. If radio surveys reveal many small halos hosting gas, the halo population may be richer than optical light suggests. If even radio surveys find few systems, the underdensity may be deeper. Simulations predict that void interiors contain substructure in the form of low-mass halos and tenuous filaments. These structures are the remnants of initial fluctuations that were not erased. Gravity amplifies all fluctuations, but in underdense regions, amplification is slower. Small-scale structures still form but later and at lower masses. This means that some of the smallest halos may form at times when the ultraviolet background is strong, making it harder for them to accrete and cool gas. Such halos can remain dark. This is one reason a void can look emptier than its dark matter content would imply. The presence of dark halos without galaxies is not directly observable, but it can leave indirect signatures. For instance, if there are many dark halos, they can slightly affect the distribution and motions of the galaxies that do exist. They can also contribute to weak lensing. In principle, they can produce subtle perturbations in stellar streams within galaxies, but such tests are not practical at the distances of the Boötes Void. The main practical test remains statistical, comparing observed void properties to simulations that predict both the dark matter and the galaxy distribution. The claim that something found in the Boötes Void does not fit any model often implicitly assumes that the void's galaxy emptiness directly represents a mass emptiness. This assumption is not always justified. In the standard picture galaxy bias means galaxies are more clustered than mass. In low-density regions, the bias can be stronger because the formation of luminous galaxies is more suppressed. Thus, a region that is moderately underdense in mass can be extremely underdense in galaxies above a given brightness threshold. This effect can make a void appear more dramatic in surveys than it is gravitationally. Therefore, a model evaluation must compare, like galaxy-defined void statistics, should be compared to mock catalogues from simulations processed with the same selection and luminosity limits not to raw mass fields. When this is done, extreme galaxy voids can arise naturally even when the mass void is less extreme. There are still potential sources of genuine tension. If the Boötes Void were found to be both extremely empty in galaxies and extremely underdense in mass, to a degree that is statistically inconsistent with the initial fluctuation distribution implied by the cosmic microwave background that would challenge the standard framework. Such a challenge would not necessarily require abandoning gravity or dark matter, but it could point to issues in parameter values or to the need for more complex initial conditions. Another possibility is that the void's mass profile or dynamics differ from predictions in a way that cannot be reconciled by galaxy bias and selection. For example, if outflow velocities implied a mass deficit much deeper than allowed, or if lensing indicated an anomalous mass distribution. However, these tests are difficult for a single void, and uncertainties are large. Within current practice, the dark matter description of a void emphasizes that the void is part of the cosmic web with a diluted dark matter field rather than an absence. The interior contains fewer massive halos, many low-mass halos, and weak filaments. The visible galaxy inventory samples only a fraction of this structure. The diffuse gas traces another fraction. Gravitational methods aim to measure the mass field directly, but often require stacking or statistical approaches that are better suited to void populations than to single-named voids. For Boötes, the dark matter picture remains a model based on the combination of observed galaxy scarcity, the surrounding rim structures, and the general success of simulations in reproducing void statistics. The most cautious statement is that Boötes is an extreme but plausible expression of the underdense tail of the cosmic density field, and that its apparent emptiness in light does not automatically imply an equally extreme emptiness in mass. Having established the role of dark matter in shaping the void interior, the next inward step is to focus on dynamics more directly, not as a general outflow expectation, but as a measurable pattern of motion and expansion within and around the void that can be used to test whether the Boötes region behaves as models predict when measured through velocity fields and redshift space distortions. The next inward region is the void's dynamics, where the Boötes Void is treated not only as a static deficit of galaxies, but as a region with characteristic motions that arise from gravity acting on an underdense mass distribution. In standard structure formation, the density field and the velocity field are linked. Where mass is over dense matter tends to flow inward and collapse. Where mass is under dense matter tends to flow outward because there is less gravitational pull to counter the general expansion. This produces a coherent pattern, often described as a void outflow. The outflow is not an explosion and not a separate expansion. It is a relative effect compared to average regions, galaxies near the void. Interior recedes slightly faster from one another and from the void center. Over cosmic time, this helps evacuate matter from the void and build up the surrounding walls and filaments. If the Boötes Void is as deep in mass as its galaxy deficit suggests, Models predict a certain amplitude and spatial pattern for this outflow, and these predictions can be tested through observations, though the tests are indirect and limited by sparse tracers. A key concept is peculiar velocity, the velocity a galaxy has in addition to the smooth recession expected from cosmic expansion. Peculiar velocities are driven by gravitational acceleration from the surrounding mass distribution. In and around a void, peculiar velocities tend to point outward from the void center, reflecting the mass deficit. The magnitude is typically a few hundred kilometers per second or less, depending on void size and depth, which is small compared to recession speeds at hundreds of millions of light years, but still large enough to affect redshift measurements. Because redshift includes both cosmic expansion and peculiar velocity along the line of sight, the observed galaxy distribution in redshift space is distorted. These distortions can be measured statistically. For a void, the characteristic distortion involves an apparent stretching or squashing of structures when viewed along the line of sight relative to the void center. If galaxies are flowing outward, the redshift space positions can be shifted, altering the apparent void shape. Analysts model these effects to infer the underlying velocity field. Direct measurement of peculiar velocities requires independent distance indicators such as standard candles or standard rulers that provide distance without relying solely on redshift. For individual galaxies at the distance of the Boötes Void, these measurements are challenging. Distance indicators that work well nearby become uncertain at larger distances, and the void's distance range is large. As a result, direct peculiar velocity mapping of Boötes is limited. Instead, the primary approach is statistical inference from galaxy clustering in redshift space, and from comparisons to simulations. One method considers the cross-correlation between void centers and surrounding galaxies. By measuring how galaxy density varies around voids in redshift space, and fitting models that include both density and velocity, analysts can estimate the outflow profile. This method works best for large samples of voids. For a single void, it can still be informative if there are enough galaxies around its boundary, but uncertainty remains significant. Another dynamic test is the Alcock-Pogzinski effect applied to voids. In principle, if a void is statistically spherical in real space, when averaged over many voids, then any observed anisotropy in its shape in redshift space can be used to test cosmological parameters and velocity models. This again requires stacking many voids, not relying on a single named void. For Boötes, which may not be perfectly spherical, and which is identified in a specific survey volume, this method is less direct. Still, the general principle matters. Void dynamics are encoded in how void shapes appear in redshift space, and model predictions for those distortions provide a test of the underlying cosmology. Within the standard framework, the expected velocity field around a large void has a specific radial dependence. Near the center, the density is lowest, and the outflow is strongest relative to average, but the observable traces are few. Moving outward, the outflow decreases as one approaches the boundary where density rises. Near the boundary, matter can pile up, and in some models there can be a compensating overdensity ridge. The velocity field can show a transition where the outflow slows and may approach zero beyond the ridge. In some cases, depending on the surrounding environment, there can be infall into nearby overdense structures that competes with the void outflow. For Boötes, which is embedded in a complex web, the velocity field is likely to be anisotropic, with stronger outflow in directions where the void is deeper and more isolated and weaker outflow toward nearby massive structures. This anisotropy makes it difficult to summarize the void dynamics with a single radial profile, but it is also a prediction. Voids in realistic environments are not perfect spheres with perfectly radial flows. Claims a model mismatch could arise if inferred outflow velocities are inconsistent with the void's measured density profile. For example, if the galaxy distribution suggests a deep void, but the inferred velocity distortion suggests only weak outflow, that could imply that the mass deficit is not as deep as the galaxy deficit, reinforcing the role of galaxy bias. Conversely, if velocity distortion suggests strong outflow, but galaxy count suggests a less extreme void, that could imply either an undercount of galaxies, perhaps due to selection effects, or an unusually deep mass void. These interpretations depend on accurate modelling of bias redshift errors and survey geometry. Redshift measurement errors can smear positions and reduce apparent distortions. In sparse regions, shot noise can create apparent features that do not reflect the true velocity field. Therefore, dynamic inferences must be treated as probabilistic rather than definitive. There is also a connection between void dynamics and the growth rate of structure in the universe. The growth rate describes how quickly density contrasts grow over time, and it depends on the content of the universe, including dark matter and dark energy. Voids provide a complementary probe to clusters because they respond to the same growth physics, but in an underdense regime. If the growth rate were different from the standard expectation, the velocity field around voids could differ. Some studies use void dynamics in large surveys to test gravity on large scales. These tests typically find consistency with standard gravity within uncertainties, though the details depend on survey and method. For a single void like Boötes, such a test is not as powerful, but the concept highlights that void dynamics are not merely a curiosity. They are a measurable consequence of cosmological physics. In the Boötes context, the most practical dynamic information comes from the distribution of galaxies around the void edge and how their redshift space positions define the void's shape. If the void appears elongated along the line of sight, that could reflect peculiar velocities or survey artifacts. If it appears compressed, that could reflect different velocity patterns. Analysts compare the observed pattern to mock surveys generated from simulations that include both cosmological expansion and peculiar velocities. These mocks also include the same selection effects as the real survey. A match suggests that the void's dynamics are consistent with standard expectations. A mismatch suggests either observational systematics or, more interestingly, that the void's mass profile or surrounding environment differs from what the model assumptions capture. At this inward stage, dynamics are the bridge between structure and physics. The Boötes void is expected to have an outflow pattern that reflects its mass under density, but measuring that pattern is difficult because traces are sparse and because redshift space distortions are subtle. A careful approach treats any inferred velocity signal as a constraint with uncertainties, and it compares it to simulations processed through the same observational pipeline. The next inward step is to define more sharply what kinds of observations are often labelled as anomalies in void studies, and what would be required for such observations to rise from impression to genuine statistical tension with established models. When a void is described as containing something that does not fit any model, the phrase often compresses several different kinds of observations into a single dramatic claim. To examine that claim carefully, the next inward region is the category of reported anomalous signals associated with the Boötes void, and with large voids more generally, and the specific conditions under which such signals would represent true tension rather than a misunderstanding or a mismeasurement. An anomaly in this context is not simply an observation that is unusual. It is an observation that remains inconsistent with model predictions after accounting for measurement, uncertainties, selection effects, and the statistical expectation that rare structures exist in large samples. Because void interiors are sparse, many apparent anomalies arise from the same root cause small numbers. With few galaxies, each additional object has a large effect on inferred density, clustering, and property distributions. With few background sightlines, each absorption detection or non-detection carries disproportionate weight. With low lensing, signal noise and systematics can dominate. Therefore, the first step in defining any anomaly is to specify what is measured, how it is measured, what the model prediction is for that measurement and what uncertainty is attached to both. One class of claimed anomalous signals involves galaxy distribution itself. A void might be said to be too large, too empty, or too sharply bounded compared to expectations. The core measurement is the void size distribution and depth distribution, predicted by simulations for a given survey volume. A genuine anomaly would require that given the survey volume and selection, the probability of finding such a void under the model is extremely low. In practice, this requires careful accounting for the look. Elsewhere, affect the fact that if one searches many regions of the sky and many distance ranges, some extreme structure is likely to appear somewhere. A void can look model-breaking if one treats it as a unique object discovered without a search, but if it is the most extreme among many candidates, its extremeness is expected. For Boötes, which has been highlighted historically as a particularly prominent void, the question becomes how its extremeness compares to the tail of the void distribution in modern surveys and simulations. The answer depends on definitions and on sample volume. This is why size alone rarely provides decisive tension. It is sensitive to method and to the statistical framing. A second class of signals involves galaxy properties inside the void. Claims may focus on galaxies that appear too massive, too evolved, or too active for such an environment, or on galaxies with properties that appear too primitive, such as extremely low metallicity suggesting isolation from enrichment. To evaluate these claims, one must compare void galaxies not to the average galaxy population, but to a model conditioned on environment and halo mass. A massive galaxy in a void could imply the presence of a relatively massive halo, which is rare but not impossible. The key is frequency. If many massive galaxies existed deep inside the void core, that would be harder to reconcile. If only one exists, it might be a statistical outlier or a boundary misclassification. Similarly, a galaxy with very low metallicity could indicate slow evolution or recent accretion of pristine gas, both plausible in void environments. The anomaly would be if such galaxies were so common that standard galaxy formation models could not produce their abundance, given the predicted halo population and accretion histories. A third class of signals involves the diffuse gas, especially absorption features. An apparent anomaly could be unexpectedly strong hydrogen absorption, suggesting denser gas than expected in the deepest interior, or unexpectedly strong metal absorption, suggesting higher enrichment than expected. The model expectation is statistical void. Sightlines should on average show weaker absorption, but internal filaments can still produce stronger lines. With few sightlines, one or two strong absorbers can seem surprising. Evaluating tension requires many sightlines or careful modelling of the probability distribution of absorbers given the void's internal structure. Another potential anomaly is the opposite, an absence of absorption where models predict some. This could occur if the neutral fraction is lower due to stronger ionization, or if the gas is more diffuse. Again, the interpretation depends on ionization modeling, which can carry large uncertainty. An absorption-based claim becomes stronger if multiple independent sightlines show consistent deviations that cannot be explained by reasonable ranges of ionization conditions. A fourth class involves gravitational probes such as lensing or integrated background signals. In some contexts, voids have been discussed in relation to temperature fluctuations in the cosmic microwave background, through the integrated Sachs-Wolf effect, where evolving gravitational potentials can imprint temperature shifts on microwave background photons. Claims of a void associated with an unusually large temperature anomaly have appeared in the broader void literature. For Boötes specifically, a similar idea would be that large mass under density produces an unusually strong temperature imprint. The integrated Sachs-Wolf signal is small in the standard model and is noisy because the microwave background has intrinsic fluctuations. A claimed anomaly would require a statistically significant correlation between the void and a temperature feature beyond what the model predicts. Such tests are sensitive to analysis choices and often require stacking many voids to detect a signal at all. For a single void, the chance alignment with a microwave background feature can mislead. Therefore, a model-breaking claim here would require careful statistical handling and replication across independent datasets. A fifth class involves internal clustering, or the presence of a structure within the void that seems too coherent. For example, if galaxies inside the void formed a dense group or a pronounced filament that appeared inconsistent with an under-dense mass field. In simulations, internal filaments exist, but they are weak. An anomaly would be if the internal structure implied a mass concentration that, if real, would significantly reduce the void's mass under density, contradicting its galaxy-defined emptiness, or if it implied an unexpected level of small-scale power in the initial conditions. Again, boundary definition matters. Many apparent internal structures can be explained by the void being defined too broadly, including regions that are only moderately underdense and that naturally contain filaments. To move from impression to true anomaly, several criteria are needed. The measurement must be robust to survey completeness and systematics. The sample definition must be clear, including how the void boundary is defined and how membership is assigned. The comparison must be made to mock observations drawn from simulations that match the survey selection, not to an abstract idealization. The statistical significance must account for multiple testing if the anomaly is found after searching. The result should be consistent across independent surveys or methods. Without these claims remain suggestive rather than decisive. In the Boötes narrative, the phrase does not fit. Any model often functions as shorthand for a sense of extreme emptiness, combined with occasional objects that appear unexpected. The disciplined approach treats the void as a test case for the interplay of cosmology, galaxy formation, and observation. It asks whether the reported signals exceed the allowed range of the standard framework given uncertainties. In many cases, what appears anomalous can be reclassified as a consequence of sparse sampling, biased traces, or definition choices. In some cases, the signal can point to shortcomings in galaxy formation modelling rather than in cosmology itself. The next inward step is therefore to examine the specific sources of systematics that can mimic surprises in void studies, because understanding these pitfalls is essential before any claim can be elevated from curiosity to genuine tension. The most common reason a void claim seems to defy models is not that physics fails, but that measurement and interpretation are stretched by sparse data. In the interior of a large void, every observational step is vulnerable to systematics that can mimic emptiness, exaggerate contrast, or manufacture patterns that appear significant. The next inward region is therefore the set of systematics specific to mapping and interpreting the Boötes Void and similar structures. These systematics are not minor details. They determine whether the observed distribution of galaxies and gas is an accurate representation of the underlying matter field, or a distorted picture shaped by survey limitations. Because the Boötes Void is large and nearby enough to have been studied across multiple generations of surveys, it provides a clear example of how systematics evolve as data improve, and how earlier impressions can persist even when methods change. A primary systematic is selection by brightness and surface brightness. Galaxy surveys often set a magnitude limit, a cut in apparent brightness. This cut is intended to define a sample that is complete to a given distance. However, completeness in magnitude does not guarantee completeness in surface brightness. A galaxy with diffuse light can fall below detection thresholds even if its total brightness is above the nominal limit, because detection algorithms depend on contrast against the background. Low surface brightness galaxies are particularly relevant in void environments where galaxies may be small, diffuse, and slow forming. If such galaxies are missed, the void appears emptier than it truly is. Correcting for this requires either specialized searches for diffuse systems deeper imaging or alternative tracers such as neutral hydrogen surveys. Even when such corrections are attempted, they can be incomplete because the population of low-surface brightness galaxies is not fully characterized at the distances relevant for Boötes. Therefore, any claim about the absolute galaxy count in the void must be framed in terms of the survey's detection limits and the possibility of a hidden population. A second systematic is redshift incompleteness. Not every galaxy detected in imaging has a measured redshift. Spectroscopic follow-up can be limited by fiber collisions, where two galaxies close together on the sky cannot both receive a fiber in the same observation by limited observing time and by observational failures when spectra are too faint or featureless. In dense regions, incompleteness can cluster because fiber collisions are more common where galaxies are close. In sparse regions, incompleteness is less clustered, but can still be uneven due to observing strategy. If a region of the sky receives less spectroscopic coverage, it can appear as a void in three-dimensional maps, even if imaging shows many galaxies. Modern surveys model this through completeness masks and weights, but early void identifications can be influenced by uneven coverage. For Boötes, which was recognized as a prominent underdensity, the persistence of the void across multiple surveys reduces the likelihood that it is purely a spectroscopic artifact, but incompleteness still affects the detailed census of interior galaxies and the sharpness of the boundary. A third systematic is distance error and redshift space distortion. Even with precise redshift measurements, galaxy positions in redshift space include peculiar velocities. Near dense structures, random motions within groups and clusters can smear positions along the line of sight, creating elongated features that can intrude into or out of the void region, depending on how boundaries are drawn. Near a void, coherent outflows can shift galaxies in redshift space, altering the apparent shape and depth of the void. If these effects are not modelled, a void can appear larger or smaller than it is in real space. Additionally, the conversion from redshift to distance depends on assumed cosmological parameters. For nearby distances, the effect is small, but it is not zero. In the Boötes distance range, the dominant issue remains peculiar velocity, not parameter choice. Analysts mitigate this by smoothing the density field on scales that reduce the impact of small-scale velocities, and by comparing redshift space voids to redshift space predictions from simulations rather than to real space predictions. Survey geometry and masking form another major source of false emptiness. Surveys avoid regions around bright stars have gaps between observing fields and cover irregular footprints. The resulting mask can carve out complex patterns in the sky where galaxies are not observed. If void-finding algorithms do not incorporate the mask correctly, they can identify voids that coincide with unobserved regions. Even when the mask is included, the effective volume near survey edges can be misestimated because the algorithm may treat unobserved space as empty or may artificially truncate structures. For a large nearby void which spans a substantial angular area, edge effects can be significant if the survey footprint cuts across the region. One safeguard is replication in multiple surveys with different footprints. Another is the use of random catalogues that follow the mask and allow density estimates corrected for geometry. A careful Boötes analysis must specify the survey footprint and demonstrate that the void is not aligned with major masked regions. Foreground extinction from Milky Way dust can also mimic galaxy deficits. Dust absorbs and reddens light-making background galaxies dimmer. If extinction is higher in a particular sky region, fewer galaxies above a fixed magnitude limit will be detected there. Surveys correct for this using dust maps, but corrections can have uncertainties, especially near complex dust structures. If extinction corrections are imperfect, a region can appear slightly underdense. For a void as deep as Boötes extinction alone is unlikely to explain the full deficit, but it can contribute to the detailed shape and can bias counts, particularly for faint galaxies near the detection threshold. Systematics also arise from the definition of the void itself. Different void finders produce different void catalogues. A method that identifies the deepest underdensity core will yield a smaller, deeper void. A method that follows connected underdense regions can yield a larger, shallower void. When a void is named and discussed as a singular object, these differences can be overlooked, leading to inconsistent comparisons. A claim that Boötes is too large may refer to a broad connected underdensity. A claim that it is too empty may refer to the core. If these are mixed, the claim can seem stronger than it is. A rigorous approach defines the void consistently and matches the definition in simulations and in observations. Small number statistics, often called shot noise, amplify all of these issues. In a region with few galaxies, random fluctuations in counts are large in fractional terms. A difference of a few galaxies can change the inferred density by a significant percentage. This can create the appearance of internal structure such as a filament or a cluster, where the pattern may be consistent with randomness. Statistical tools can address this, but they require careful modelling of the expected distribution under the null hypothesis. Human pattern recognition can easily overinterpret sparse maps. This is especially true for early void studies that relied on visual inspection of galaxy distributions. Modern methods reduce subjectivity but still face the fundamental limit that sparse data yield noisy inferences. Calibration systematics also matter for galaxy properties. Metallicity estimates depend on emission line ratios and on calibration methods that can shift values systematically. Star formation rates depend on assumptions about initial mass functions and on corrections for dust. Gas mass estimates from radio emission depend on distance and on conversion factors. In a void environment where galaxies may have low dust and low metallicity, standard calibrations may be less reliable. If an interior galaxy appears to have an extreme property, part of that extremeness may be calibration bias rather than physical difference. Confirming extremes requires multiple independent traces and careful cross-checks. Taken together, these systematics provide a coherent explanation for why void claims often sound stronger than the underlying evidence supports. They do not imply that voids are not real. They imply that voids are delicate objects to measure. The Boötes Void remains a prominent underdensity across surveys, but the precise census of its interior galaxies, the sharpness of its boundary and the extremeness of its properties depend on how these systematics are handled. This perspective sets up the next inward step, which is statistical framing. Even with perfect measurements, one must ask how a single extreme structure should be interpreted within a probabilistic universe, and how to distinguish genuine model tension from the expected existence of rare tails in large samples. After systematics, the next inward region is the statistical meaning of a single extreme void. Even if every observational bias is addressed, the interpretation still depends on probability, because the large-scale structure of the universe is not deterministic in the sense of producing one fixed pattern. It is a realization of a random field shaped by initial conditions and by gravitational growth. In such a field, extremes are expected. The question is not whether an extreme exists, but whether it is too extreme given the model and the surveyed volume. This distinction is often lost in popular phrasing. A statement that a void does not fit any model implicitly treats the model as predicting a narrow range of outcomes. In reality, the model predicts distributions. Voids have a range of sizes, depths, shapes, and internal structures. A single void is one draw from that distribution. Determining whether it is inconsistent requires placing it in the context of many draws, real or simulated, and asking where it sits in the tail. A basic concept is cosmic variance. Cosmic variance is the idea that measurements made in one finite region of the universe can differ from the global mean simply because the region is a particular realization of the underlying random field. Even if the model is correct, one region can contain an unusually large cluster or an unusually large void by chance. The amplitude of cosmic variance depends on the scale of the measurement and the survey volume. For very large volumes, the average approaches the global mean, and extremes become less influential. For smaller volumes, extremes can dominate. The Boötes Void is large, but the relevant question is the volume of the survey within which it is identified. If the survey volume is modest, finding one large void may not be surprising. If the survey volume is huge, and yet Boötes is still an outlier beyond model expectations, that would be more notable. Therefore, the appropriate statistical framing begins by specifying the effective survey volume and selection, then comparing the void's properties to the distribution of voids expected in that volume. Another concept is the look elsewhere effect. If a researcher searches across many positions and distances and selects the most extreme underdensity, the probability of finding an extreme is higher than if the structure was specified in advance. Many named structures are discovered by scanning maps either visually or algorithmically. This is normal in exploratory science, but it means that naive probability estimates can be misleading. An extreme chosen after searching cannot be treated as a random draw. It is the maximum of many draws. The correct comparison is then to the distribution of maxima in a survey, not to the distribution of typical voids. This is one reason early claims of model-breaking structures often soften when the statistical context is clarified. The discovery process itself inflates extremeness. Void statistics also depend on how voids are defined. A void defined by galaxy counts above a certain brightness threshold is not the same as a void defined by total mass density. The distribution of galaxy-defined voids depends on galaxy bias and on the selection function. If one changes the brightness threshold, the void catalogue changes. Brighter thresholds yield fewer galaxies and can produce larger and emptier apparent voids. Deeper thresholds yield more galaxies and can break large voids into smaller subvoids. Therefore, the statistical distribution of voids is conditional on the tracer population. For Boötes, early surveys were relatively shallow by modern standards, which can make the void appear more dramatic. Modern, deeper surveys can reveal more internal galaxies and structure. This does not necessarily mean the void shrinks in mass. It means the tracer changes. A valid statistical comparison must match tracer definitions between observation and simulation. Because of these dependencies, a common approach is to create mock catalogues from simulations. A simulation is initialized with density fluctuations consistent with the cosmic microwave background and evolved under gravity, producing a cosmic web. Galaxies are then assigned to dark matter halos using models that reproduce observed galaxy clustering and luminosity functions. The simulated galaxies are then subjected to the same selection and geometry as the real survey. This produces a mock survey in which voids can be identified using the same algorithm. One can then ask how often voids like Boötes appear in the mocks. If they appear with reasonable frequency, Boötes is consistent. If they appear extremely rarely, there may be tension. The strength of this approach is that it incorporates bias selection and geometry. The weakness is that it depends on the realism of the galaxy assignment model. If the model fails in void environments, the predicted void distribution could be wrong, even if the underlying cosmology is right. Thus, an apparent tension could point to galaxy formation modeling rather than cosmological failure. Significance is also sensitive to which void property is tested. If one tests only diameter, one gets one distribution. If one tests density, contrast, one gets another. If one tests both, the joint distribution matters. A void can be large but not extremely empty in mass, or extremely empty in galaxies but moderate in mass. It can have an unusual shape due to surrounding structures. It can have an internal filament that makes it less homogeneous. Each of these properties has a distribution. A claim that something does not fit any model often combines properties without accounting for their correlations. For example, larger voids tend to be less deep in mass than smaller, more compact voids depending on definition. If a void is both very large and very deep, that combination might be rarer than either property alone. Statistical evaluation must therefore specify which combination is being claimed and whether the combination is measured robustly. Another statistical issue is confirmation bias in interpreting sparse data. In a sparse region, one can tell many stories about the few objects that exist. A single unusual galaxy can be seen as evidence of unexpected physics. But in large surveys, unusual galaxies exist everywhere. The correct question is whether their rate is different in the void. This requires controlled samples and careful matching in mass and observational completeness. Without this, anecdotes replace statistics. For the Boötes Void, the most informative comparisons involve matching void galaxies to field galaxies of similar mass and observing depth, then measuring differences in distributions of star formation, rate gas fraction, and metallicity. These differences can then be compared to simulation predictions. This is a statistical program, not an individual object narrative. Within cosmology, a void like Boötes can be used as a constraint on parameters, but it usually provides a weak constraint compared to the cosmic microwave background, large-scale clustering and lensing. This is because void statistics have larger uncertainties and depend more on galaxy bias. Therefore, even a somewhat unusual void rarely forces a major model revision. Instead, it invites better measurement and larger samples. A single void can still be valuable as a testbed for methods, as a target for deeper surveys, and as a case study in how environment shapes galaxies. The probability framing ensures that excitement remains aligned with evidence. In sum, the statistical meaning of Boötes is that it must be evaluated as part of a distribution, not as a singular challenge. The standard model predicts that rare voids exist, especially in large volumes. The appropriate test is whether Boötes lies within the model's tail once selection definitions and the search process are accounted for. If it does, the void is not a failure of cosmology, but a feature of its randomness. If it does not, the next step is to ask whether the tension arises from cosmological parameters from the modelling of galaxy formation in low-density environments or from subtle systematics. With this statistical framework in place, the next inward step is to clarify what the standard cosmological model predicts in more concrete observational terms for void profiles and evolution, so that any claim deviation can be stated precisely in the language of observables rather than in broad impressions. With statistical framing established, the next inward region is the set of concrete model-level predictions that connect the standard cosmological framework to observables in and around a void like Boötes. The standard framework describes a universe dominated by dark matter and dark energy, with ordinary matter as a smaller component. It predicts an initial pattern of density fluctuations with specific statistical properties, and it predicts how those fluctuations evolve under gravity in an expanding background. From this, it yields predictions for the abundance of voids, their density profiles their growth over time, and their imprint on the distribution and motions of galaxies. These predictions are not exact for any one named void, but they are precise in the sense that they can be tested statistically, and in some cases for individual prominent structures with suitable data. One concrete prediction is the void density profile in mass. In simulations, voids tend to have a low density core and a rising density toward the boundary. The core density depends on void definition, but for large voids, the mass under density is typically moderate rather than extreme. This means that the mass density might be in qualitative terms tens of % below the mean rather than near zero. In contrast, the galaxy density, especially for bright galaxies, can be much lower. This difference is a model prediction, arising from bias, and from the suppression of luminous galaxy formation in low-density environments. Therefore, the standard model predicts that a galaxy-defined void can appear nearly empty even if the mass is not. The practical observable consequence is that when one compares a void found in a bright galaxy sample to a void found in a fainter sample, the bright sample void will appear larger and emptier. Another consequence is that weak lensing measurements should indicate a shallower deficit than galaxy counts suggest. If lensing were to indicate a deficit as deep as the galaxy deficit, that would challenge the bias expectations and might indicate an unusually deep mass void. A second prediction concerns the compensation around voids. Many voids exhibit a ridge of higher density near the boundary where matter has accumulated. Whether a void is compensated depends on its environment. A compensated void has an overdense shell, such that the total mass deficit within a certain radius is balanced by excess mass in the shell. An uncompensated void does not fully balance and represents a net underdensity on larger scales. This distinction matters for large-scale gravitational potential and for any integrated effects on background radiation. The standard model predicts a mix with compensation depending on void size and surrounding structure. Large voids can be less compensated and can connect to broader underdense regions. For Boötes, the surrounding walls and filaments suggest some compensation locally, but whether it is fully compensated in mass is an empirical question. Observationally, compensation influences the void galaxy density profile beyond the boundary and affects the velocity field. A compensated void can show a change in velocity pattern near the ridge. A third prediction is the void velocity profile. In the standard model, the coherent outflow is linked to the integrated mass deficit. The outflow is expected to be strongest near the inner region and to diminish toward the boundary, with possible features near a compensating ridge. Redshift space distortions encode this pattern. For a given density profile, simulations predict a corresponding velocity profile. Therefore, a joint measurement of density in redshift space, anisotropy, provides a test. If the measured anisotropy is inconsistent with the measured density profile under standard gravity, that would point to either measurement error, bias modeling error, or potentially modified gravity. However, because galaxies are bias tracers and redshift distortions are noisy in sparse regions, the standard approach is to test consistency across many voids rather than relying on one. A fourth prediction is the evolution of voids over time. Voids grow in comoving size and deepen in relative underdensity as the universe evolves, particularly at earlier times when structure growth is faster. At late times, dark energy slows the growth of structure and void evolution becomes more gradual. The standard model predicts how void size distributions change with redshift. In principle, by studying voids at different distances, one can test this evolution. For a nearby void like Boötes, the direct evolution is not observable in real time. Instead, one compares Boötes to voids at higher redshift in surveys and to simulation predictions. If the present-day abundance of large voids is inconsistent with the model's predicted evolution that could indicate parameter tension, most current constraints find broad consistency with uncertainties dominated by tracer selection and survey limitations. A fifth prediction relates to galaxy properties as a function of environment. The standard model itself does not specify star formation rates. That requires galaxy formation physics. Yet when galaxy formation models are embedded in the standard cosmology, they predict that void galaxies should at fixed stellar mass have certain tendencies: higher specific star formation, higher gas fractions, lower metallicities, and more disk-dominated morphologies on average. These are not absolute, and the scatter is large. The key is that the model predicts environment-dependent distributions. For Boötes, observing these distributions helps test galaxy formation models. A mismatch here is more likely to indicate incomplete baryonic physics than a failure of cosmology. For example, if void galaxies are predicted to be too quiescent compared to observations, the model may be overestimating feedback strength or underestimating gas accretion in low-density environments. If they are predicted to be too active, the model may be underestimating the impact of the ultraviolet background on small halos, or overestimating molecular gas formation efficiency at low metallicity. A sixth prediction concerns the relationship between voids and the cosmic web's connectivity. In simulations, large voids are not isolated spheres, but are connected through lower density channels, and are bordered by filaments that connect to the broader web. The standard model predicts that voids have internal structure, but it is weaker than outside. Therefore, the presence of some internal alignments of galaxies is expected. The observable test is whether the internal structure level measured by clustering and by the distribution of galaxy orientations matches simulation predictions. Again, a single void provides limited statistics, but it can be a target for deep mapping that improves the sample size. In practical terms, these predictions establish what can be measured and compared. Mass profiles through lensing, even if noisy, provide a direct link to dark matter. Velocity profiles through redshift space distortions connect to gravity and growth. Galaxy density profiles connect to bias and selection. Gas absorption statistics connect to baryon distribution and ionization. The model predicts coherent relationships among these observables. A claim of not fitting any model must specify which relationship is broken. Is the mass profile too deep? Is the velocity field inconsistent with the density field? Are void galaxies too massive or too clustered? Is the gas too enriched or too dense? Without this specificity, the claim remains a general impression. At this inward stage, the standard model is not a vague statement that voids exist. It is a structured set of linked predictions for density motion and tracer behavior. This structure is what allows careful testing. The final inward step is to consider alternative explanations that remain within known physics, especially astrophysical processes and environmental effects that can make a void look more dramatic, or can shape the properties of its galaxies without invoking new cosmology. This allows the narrative to close by identifying what must be measured next, to decide whether Boötes reflects normal extremes or points to an unmodelled process. The innermost region of the topic is not a smaller physical layer inside the void, but the most specific layer of explanation, the set of alternative conventional mechanisms within established physics that can account for why the Boötes void appears as it does, and why particular observations inside it can feel model-resistant. These mechanisms operate at the interface between cosmology and astrophysics, where the large-scale mass field sets the environment, but the visible outcome depends on how gas cools formed stars and responds to radiation and feedback. The standard cosmological framework provides the scaffolding for void formation, but the appearance of a void in galaxy light is shaped by galaxy formation efficiency and by observational choices. Therefore, many apparent conflicts can be softened or resolved by examining the ordinary physics that affects detectability, and by clarifying which quantity is truly being compared to a model. A central conventional explanation is tracer bias combined with star formation suppression in low-mass halos. In void interiors, the halo population shifts to lower masses. Many of these halos sit near or below thresholds, where gas accretion and cooling become inefficient under the ultraviolet background. When gas cannot cool effectively, it cannot form a stable cold phase that leads to stars. The halo may contain some diffuse gas but little starlight. In optical surveys, such halos are invisible. Even in radio surveys, if the neutral fraction is low or the gas is diffuse, detection can be difficult. The result is that a void can contain more dark matter structure and more baryonic mass than its galaxy count suggests. This explanation does not require any change in cosmology. It requires only that galaxy formation becomes less efficient in underdense environments, which is expected. The practical consequence is that a void defined by bright galaxies is not a direct measure of mass emptiness. Any claim that the void is too empty must specify whether the claim is about galaxies, baryons, or total mass. A second conventional mechanism is the influence of the ultraviolet background and reionization history on small halos. The intergalactic medium is ionized and warmed due to ultraviolet radiation, and this suppresses gas accretion into small gravitational wells. The strength of suppression can vary with time and with local environment, because the ultraviolet field is not perfectly uniform. In dense regions, local sources can dominate, but in voids the background may be lower in intensity while the gas density is also lower, changing equilibrium ionization. Depending on the balance, small halos in voids could either retain more gas than expected, or be more strongly prevented from cooling if their potential wells are shallow. This can shift the population of faint galaxies. If galaxy formation models assume a uniform ionizing background and apply suppression thresholds that are too simple, they may mispredict the void galaxy population. A mismatch here would reflect an astrophysical modelling limitation rather than a need for new gravitational physics. A third mechanism is feedback, the process by which star formation and active nuclei inject energy and momentum into gas. In low-mass galaxies, supernova feedback can expel gas more easily because the gravitational potential is shallow. In isolation, expelled gas may not be replenished quickly. This can produce long quiet periods and low stellar masses. Yet feedback can also create episodic star formation, where bursts occur when gas cools back and reaccumulates. If void galaxies experience feedback cycles that differ from dense environment galaxies because their gas supply is smoother and their interaction rate is lower, their observable properties can diverge in ways that models tuned to dense regions might not capture. For example, gas fractions could be higher, star formation could be more extended, and metallicity gradients could be different. These outcomes can make void galaxies look unusual, but they remain within known physics. They also imply that comparing void galaxies to field galaxies requires careful matching in mass and in observational sensitivity. A fourth mechanism concerns the internal structure of voids. Simulations predict weak internal filaments and subvoids. If a void is defined broadly, these internal structures can host the majority of the void's galaxies, creating the impression that galaxies are clustered strangely inside emptiness. This is not a contradiction. It is a reminder that void interiors are not homogeneous. A claim that a filament inside Boötes does not fit a void model might arise if the void is imagined as uniformly empty, but models do not predict uniformity. They predict a low-density web. The observational challenge is that with few galaxies, any internal filament can seem disproportionately prominent. Deeper surveys can reveal whether the filament is a real coherent feature or a sparse sampling of a smoother density field. A fifth mechanism is the effect of survey depth and surface brightness limits. If the interior is populated by low surface brightness dwarfs, the void can appear much emptier in older or shallower surveys than in deeper modern data. A dramatic claim can persist if it is based on an early map that had strong limitations. As surveys improve, new galaxies can appear in the inventory without changing the underlying mass distribution. This can make the void look less extreme and can dissolve apparent tension. Even with improved surveys, surface brightness remains a hard limit, because diffuse light is difficult to detect against the sky background. Therefore, there may always be a hidden population, and any assertion of near-total emptiness must be framed as emptiness above a detection threshold. A sixth mechanism is environmental dependence in the relationship between galaxy luminosity and halo mass. In abundance matching and related methods, one often assumes a monotonic relationship between halo mass and galaxy luminosity with some scatter. In voids, this relationship may shift because gas accretion histories differ, and because feedback efficiency depends on halo growth. If the scatter increases or the normalization changes, mock catalogues built with simplified assumptions may mispredict void galaxy counts, leading to apparent model mismatch. Adjusting these relationships within plausible ranges can change predicted void properties significantly without altering cosmological parameters. These conventional mechanisms together form a coherent explanation for why the phrase does not fit. Any model can arise while the underlying cosmology remains intact. They also suggest what observations most directly decide the issue. The most decisive path is to measure the void in quantities closer to mass than to light. Weak lensing, though difficult, is one route. Another is to map gas in and around void galaxies and compare gas content to halo mass estimates, inferred from rotation curves or other dynamics. Another is to use absorption sightlines to constrain baryon density and enrichment in the void interior. Combined, these observations can determine whether the void is truly an extreme mass under density or primarily an extreme in luminous traces. After these 15 sections, the wind-down follows in the same calm neutral tone, maintaining the constraints, and allowing the topic to settle without summary or interpretation. It remains focused on what is known, what is measured, and what remains uncertain, with the sense of scale and quiet that a vast underdense region naturally invites.